Please welcome back to the stage your host, Matt Dobrige.
All right, so welcome back everybody to the Lattice Developers Conference. We're going to continue our programming, and the next session is going to be about data center security. And if you think about where all of our families spend most of their times in terms of creating content, sharing content, experiencing content, there's no greater place than to experience what it must be like to understand protecting that data than at Meta. So I'm really excited to introduce our next guest speaker from Meta, security architect responsible for Meta's hardware data center architecture. Please welcome to the stage, Mr. Indy Banerjee.
Thank you so much. Hello, everyone. I'm Indy. I work as a cybersecurity engineer at Meta, where I work to secure the data center hardware infrastructure, including both in-house and third-party silicon, as well as firmware. And in that role, I had the great opportunity to work with the Lattice team, with Jordan, with Jonathan, and Mike Greenfield, and Elena, and Maury, and of course, Mamta. So let me start by expressing my gratitude towards the Lattice team for being such great partners with Meta, and also for inviting me, giving me this opportunity to talk about one of the subjects that I'm really passionate about. We work together with Lattice to build custom silicon solutions based on the Mach-NX family of devices for the Meta server infrastructure, specifically a root of trust solution based on NIST PFR. And what I wanted to talk about today are some of the real-world challenges that we faced in integrating the solution into a massive hyperscale infrastructure such as that of Meta, and some of the key lessons that we learned along the way. All right. So cybersecurity has shaped up to become one of the top 3 strategic risks for enterprises over the last decade or so. There are estimates that cybercrime is going to cost upwards of an eye-popping $8.5 trillion by the end of 2023, and then going to shoot up even further to $10.5 trillion by the end of 2025. But I don't want to belabor the strategic significance of cybersecurity to this audience. I don't need to. Instead, what I wanted to focus on today are the distinctive characteristics of the risks that modern data centers face in terms of the threat landscape, in terms of the threat actors that we are up against. So the threat landscape for modern data centers, they include everything from a firmware backdoor on a BMC to cyber physical threats such as malware on a voltage regulator, taking down production capacity or causing a data loss event. There are several reports of mass theft of storage media, as well as IT asset seizures conducted by law enforcement agencies in other countries. There are also well-known reports of physical electronic devices, what are called hardware Trojans, being implanted into IT equipment en route to a data center, so intercepting the supply chain of the components. So in that context, what I wanted to do today was also focus on who are the hackers. One of the defining characteristics of modern data centers is the pedigree and the sophistication of the attackers that we are up against. So let's do an exercise. I want you to create a mental picture when I say the word hacker. Now, maybe 60, 70% of you are probably picturing a 20-something guy wearing a black hoodie seated in a dimly lit basement with 6 monitors running Netcat, right? Not a middle-aged Indian guy. But this Hollywood archetype of a lone wolf hacker is a relic of the past. Threat actors that we're up against today are profit-seeking enterprises. They trade zero-day exploits as a commodity in a vibrant gray market economy. There's an entire ecosystem consisting of vulnerability brokers that will find exploitable 0 days in software and sell it to exploit vendors that will then package and, in fact, weaponize these exploitable vulnerabilities into something like a PDF document that you can attach to an email. And finally, their clients include everyone from organized cybercrime to hacktivist groups to terrorist organizations and also state-sponsored and state-affiliated actors. Right? So in that context, what I want to do today is come up with a model for zero trust in the context of platform security. So unless you've been living under a rock, you've obviously heard of zero trust. It started as a reference model from NIST, the National Institute of Standards and Technology, that defined zero trust very concretely as a model in which any entity, irrespective of its location with respect to the enterprise network, only has access to certain assets, certain enterprise assets that it is authorized to, and it only has access after it has authenticated itself. And finally, the access only lasts for a session length, for a well-defined length of time. So that's a very concrete definition, but unfortunately, zero trust has now become the greatest industry buzzword in the cybersecurity industry since Internet of Things. Right? So I think what we should do today is try and create a model of what I mean when talking about platform security, and then try and see if we can apply some of these original concepts of zero trust to come up with a notion of zero trust platform security. And here's the model that I like to use. I've taken to calling it the zero trust platform security layer cake. Each layer in this model represents a distinct security objective for a cloud data center. For example, data security, the runtime, integrity of the runtime environment, trusted platform state. Each of these layers represent a cohesive subset of assets that need to be protected. And you can also map the commonly deployed security technologies, such as, say, traffic encryption or data at rest encryption, which sound very similar. You can map them to individual layers in this model. Further, this model also shows you the relationship between the layers. What I mean is, every layer, let's take the example of data security, relies on trusting every other layer below it, but not any layer above it. That's why it's a stack. So, for example, if you want to ensure the security of data on a system, you must ensure runtime integrity, trusted platform state, and so on. If, for example, you have, say, a remote access Trojan, which is receiving commands over a command and control channel from a remote server, and the adversary already has control of your runtime environment, then a service cannot trust the security of data that it stores or processes in this system. So that's all about the model. Now, when I say platform security for the rest of this presentation, I will be talking explicitly about the bottom 3 layers. vis-a-vis trusted platform state, where we deploy technologies such as continuous attestation and integrity monitoring, integrity measurements. Trusted platform identity, where we deploy technologies such as authentication of devices connected to the server. And finally, protecting the integrity of the supply chain, where we deploy things like platform certificates from vendors in order to ensure the legitimacy of devices as they connect to the data center network. So, with that context, I want to take a little step back and talk about what a modern data center operation really looks like. So, any modern data center will be anywhere between, say, a few thousand to hundreds and thousands of blade servers, rack switches, fabric switches, BMCs, power distribution units, and storage media, all interconnected with millions of feet of fiber optic cable, which provides connectivity both for management as well as for serving production traffic, right? And if you think about it, at Meta's scale, or at Google's scale, or at Microsoft scale, it is a Herculean enterprise. I'm talking about the orchestration of hundreds of automated processes for provisioning, for unprovisioning servers, for managing spare capacity, for monitoring failures, for remediation, for monitoring storage media, and so on. So in that context, what we learned working with the team at Lattice while building a custom platform root of trust solution was that if we are not extremely vigilant and aware of the issues with data center management, then we can end up negatively impacting the resiliency of the fleet. Some of the key lessons that we learned along the way can be put in 4 buckets. That's reliability, availability, serviceability, and scalability. So let's start with reliability. And I wanted to talk more about cryptographic attestation. So when a device, let's say a NIC or a root of trust, comes up and wants to connect to the data center environment, the first thing it has to do is a protocol called attestation, wherein it has to produce an unforgeable token guaranteeing the integrity of its initial platform state. So these Mark-NX devices that we had been working on, their initial platform state is essentially encapsulated within the FPGA image. Now, this involves Lattice or a vendor such as Lattice generating a signature on the initial platform state, a signature which is unforgeable, which guarantees to the client such as Meta, when we are deploying it in our data center, that this device is trusted, that this device indeed originates from Lattice, and it comes in the initial platform state that we expect it to. However, what this also means is any minor change in the FPGA image, in the initial boot up image, say, for example, a patch to fix a bug in the I2C interface, means that the entire fleet of FPGA devices, of root of trust devices, now needs to be updated, which means that their platform certificates are now invalid. Now, this tends to snowball pretty fast because downstream data center operations, fleet management operations such as, say, firmware maintenance and upgrades, these highly business-critical operations now have an upstream dependency on Lattice's FPGA image, right? So the lesson that we learned here through several trials and errors was that it's really important to have exhaustive and robust testing and validation of the initial firmware state, the initial platform state of the devices, before the devices are ever deployed in the data center. Similarly, availability is another very critical component of running a data center. One of the most critical and failure-prone operations that happen in a data center environment are secure firmware upgrades. Now, what does secure mean in this context? It means that every firmware package and every version of that firmware that is deployed in production are signed with a key that we trust. And so, for example, if a rogue insider, a rogue employee or contractor wanted to flash a backdoored firmware image into a production server, it would fail because the server only admits the right version, the trusted version of the firmware in production. But it turns out in managing a heterogeneous fleet of servers, of several million servers, it's actually not so uncommon to pick the wrong firmware version and run a maintenance train and flash it onto 500,000 servers within a span of a day, right? This is routine. So what ends up happening is I launch a maintenance train, and then suddenly I have 50,000 servers which refuse to boot up, which do not allow any debug capabilities to manually diagnose and remediate the problem in a part of the world where I don't have physical access, right? So what's missing from this picture is recoverability. Downtime, or in the data center parlance, offline capacity is a major cost factor in managing data center operations. The lesson that we learned, and in fact implemented with the help of Lattice, was we came up with a design which allowed the Mach-NX to have a fallback, and in case there was a corruption in the firmware, automatically boot up from a fallback image in SpyFlash without needing any manual intervention. And this image was also signed and trusted, so it would boot up into a trusted state all by itself. We believe that downstream, once these devices are deployed, this will end up saving thousands of person hours in manual debugging and diagnostics. All right. So the goal of serviceability in a modern data center environment is that any component or any field replaceable unit, it should be possible for a trained service technician to easily remove, replace, and service it standing in front of the rack without having to remove the whole component or remove the whole blade server and take it offline. So this means that any solution that we come up with needs to be modular, needs to be mechanically designed in a way so that it does not need any specialized mechanical tools to remove and service that part. Okay, so this is well understood, this is well established. However, what we learned is that this is not enough. Security protocols, such as ownership transfer, what I believe in the Lattice parlance is often called supply guard, also require the provisioning of unique cryptographic assets into a security module, right? So that leads to two problems. One is spare capacity. So let's say I have 5,000 field replaceable root of trust modules sitting in a data center storage for 6 months. But within the span of that 6 months, we've actually updated the production firmware version 16 times. What that means is when I take the spare FRU module out of storage and I have to plug it into the data center, if we want to do the ownership transfer at that point, the data center technician will actually have to log into the device, connect back to the vendor network, and reprovision it with a certificate so that it can retrieve the cryptographic assets from a remote server. This is a prohibitively expensive operation when it comes to managing a large data center at scale. Similarly, the second problem was that, and of course, none of these problems are unique to Meta or to Lattice. What we learned is a number of the solutions for PFR, for platform root of trust, available in the market, they actually program the root of trust keys into OTP memory, which is understandable. These keys have to be immutable. But what that also means is that if Meta wants to do another ownership transfer and wipe the slate clean, that is, revoke the credentials on these modules and resell it into the circular economy, that now becomes impossible because the keys are flashed in OTP memory, and Meta is left, or the data center provider is left with holding the check for depreciation on these assets over a long period of time. Similarly, along the same line, another goal of deploying security solutions in a data center environment is scalability, specifically the scalability of the manufacturing, testing, and assembly process. Any vendor, whether it's FPGA or ASIC vendor that wants to play a big role in the supply chain for modern data centers will have to optimize their manufacturing processes so that they have the flexibility and the scale to deliver 1 million chips or 500,000 chips on demand per quarter to a data center provider. Now, the common theme I want to draw out of these observations, these learnings, is two-parted. The first part is that no one is going to get this right in the first try, right? This is not an established solution such as TPMs. I'm talking specifically about PFR. It's not been around for that long. So, and also, the data center operations that I referred to look very, very different between the hyperscalers. So, a big advantage for using programmable solutions, such as the Mark and X FPGAs, was that we did not have to get it right on the first try. We did not have to get provisioning or attestation or protocols like DICE right the first time. And in fact, we tinkered and made changes to initial requirements, made changes based on the feedback from our operations people until the last moment in the project. The second part, as Jim already talked about, is crypto agility, but I want to generalize that to agility in enforcing security policies. Security policies are not a dormant thing. They keep changing in response to new regulations. They keep changing in response to new types of use cases, even new hardware that has to be deployed in a data center. So working with FPGAs really allowed us to tinker with the access control properties, the access control policies that we wanted to enforce in the data center environment. Because sometimes the reality is that despite our security objectives, we can have a massive failure outage in the data center, and somebody needs to go in and be able to log in to the servers and in the absence of the correct credentials or the correct keys, right? So to sum up, the point I want to make is any one of these observations, learnings, might be very obvious to people that are very experienced in data center operations. But collectively, I think a picture begins to emerge that implementing a zero trust architecture in a modern data center can have very negative impacts on operations unless we allow the flexibility of solutions such as FPGAs, such as other programmable hardware, which allow us to prototype a solution in production. And finally, I think this observation is kind of a shared realization across the industry, and it's leading to a few interesting trends that I want to just touch on at the end of my talk today. One of the big trends is standardization, with things like the DMTF standardizing version 1.2 of the SPDM protocol. What that means is hyperscalers like Meta will not need to reinvent the wheel, that is, reclue their attestation servers every time a vendor comes up with a new security protocol. A similar example is, of course, DCSCM. The second big trend I see is certification. There's a growing trend of hyperscalers sort of pushing down the burden of certifying, of doing security analysis on vendor IP or vendor devices, because what's really happening is we have to do it multiple times. Microsoft has to do it, and NVIDIA has to do it, and Google has to do it, and Meta has to do it. So instead, there's a lot of opportunity here for vendors to self-certify or work with the OCP SAFE program to get their IP, to get their devices certified so that it's data center ready. And finally, the other big trend across the ecosystem is open source. Again, this allows vendors to consolidate along a pre-certified and pre-vetted solution, such as Calyptra, which is an endpoint root of trust technology. And I believe that the convergence of these three trends provides us a big opportunity for innovation in the security space. Thank you once again, and I'd like to invite Matt back.
Hey, that was really excellent. Thank you so much, Indy. It's amazing because we all use Meta's apps more than any other apps on the planet, and knowing that Indy and the Meta architecture team have this type of a commitment to security and being part of that journey is really wonderful. So thank you again, Indy. Thank you again to the Meta team for the partnership and the opportunity to secure all of our data across all of our families.